Whether the old metal well line is an acceptable grounding electrode depends on several factors. The National Electrical Code, often referred to as the NEC, requires 2 or more grounding electrodes for new installations, one of which must be a grounding rod. The metal line must be in direct contact with the earth and continuously buried for a significant distance. The soil must have a low electrical resistance to provide effective grounding. The metal line should not be used as a current-carrying conductor. It is important to ensure that the line is not energized or subjected to electrical surges. The exposed portion of the metal line in the house should be properly insulated to prevent accidental contact. Given the safety concerns and the need to meet code requirements, it is recommended to use a grounding rod. Install a copper-clad steel grounding rod at least 8 feet long and 6 inches deep into the earth. In addition to the grounding rod, the grounding system may be further enhanced by using other electrodes such as buried copper wires and grounding rings or plates. Remove the grounding clamp from the old metal well line to ensure that it is not used as a grounding electrode. Test the grounding system using a ground resistance tester to verify its effectiveness. Consider using a surge protector to protect the electrical system from voltage spikes. Consult with a qualified electrician to ensure that the grounding system is properly installed and compliant with all applicable codes and standards. Grounding is a critical aspect of electrical safety, protecting people and property from electrical hazards. A proper grounding system provides a low impedance path for fault current to return to the source, allowing overcurrent devices like circuit breakers or fuses to quickly trip and interrupt the flow of electricity during a fault. This prevents dangerous voltage from appearing on metal parts of appliances, equipment, or the electrical system itself, reducing the risk of electric shock. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding and bonding electrical systems to ensure safety and compliance. Article 250 of the NEC covers grounding and bonding requirements. The grounding electrode system is a key component connecting the electrical system to the earth. The system typically includes 1 or more grounding electrodes, such as grounding rods, ground rings, metal underground water pipes, or concrete encased electrodes. The NEC mandates that all grounding electrodes be bonded together to form a unified grounding system, ensuring that all parts of the system are at the same potential. Grounding rods, typically made of copper or copper-clad steel, are commonly used as grounding electrodes. They must be at least 8 feet long and driven into the earth to a depth of at least 8 feet. The NEC requires that the grounding rod be installed so that at least 8 feet of its length is in contact with the soil. If rock bottom is encountered, the rod can be buried horizontally in a trench at least 30 inches deep. When using multiple grounding rods, they should be spaced at least 6 feet apart to ensure that they are in different areas of earth and provide effective grounding. Ground rings, another type of grounding electrode, consist of a bare copper conductor that encircles a building or structure and is buried directly in the earth. The ground ring must be at least 20 feet long and buried at a depth of at least 30 inches. This method provides a large contact area with the earth, resulting in low grounding impedance. Metal underground water pipes can also serve as grounding electrodes under certain conditions. The water pipe must be in direct contact with the earth for at least 10 feet, including any well casing that is bonded to a piping system. Internal metallic water piping located more than 5 feet from the point of entrance to the building cannot be used as a grounding electrode. A concrete encased electrode, also known as a UFA ground, is a grounding electrode that is encased in concrete. It consists of at least 20 feet of bare copper conductor, sized no smaller than number 4 American wire gauge, encased within at least 2 inches of concrete. The concrete must be in direct contact with the earth. This type of electrode is commonly used in new construction where the concrete foundation provides a large contact area with the earth. In addition to grounding electrodes, bonding is another essential aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a low impedance path for fault current. This includes bonding metal conduits, metal enclosures, metal water pipes, and other metal components to the grounding system. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The NEC specifies the requirements for bonding different parts of the electrical system, including the size of bonding conductors and the methods for making connections. The main bonding jumper is a conductor that connects the equipment grounding conductor to the grounded conductor at the service equipment. The equipment grounding conductor provides a path for fault current to return to the source, while the grounded conductor, typically the neutral, provides a return path for normal current. The main bonding jumper ensures that the equipment grounding system is effectively connected to the grounded conductor, providing a low impedance path for fault current. The size of the main bonding jumper is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the main bonding jumper based on the size of the service entrance conductors. In addition to the main bonding jumper, equipment grounding conductors are used to connect metal parts of equipment and appliances to the grounding system. These conductors provide a path for fault current to return to the source in the event of a fault. The size of the equipment grounding conductor is determined by the rating of the overcurrent device protecting the circuit. The NEC provides tables that specify the minimum size of the equipment grounding conductor based on the rating of the overcurrent device. Ground fault circuit interrupters, or GFCIs, are another important safety device used in electrical systems. GFCIs are designed to detect small imbalances in current between the hot and neutral conductors, which can indicate a ground fault. When a ground fault is detected, the GFCI quickly trips and interrupts the flow of electricity, preventing electric shock. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. The NEC specifies the locations where GFCIs are required, as well as the requirements for their installation and testing. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning, utility switching, or other transient events. SPD divert excess voltage to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the service entrance and at branch circuits to provide comprehensive surge protection. The NEC provides guidelines for the selection and installation of SPD, including the requirements for their grounding and bonding. Electrical inspections are an important part of ensuring the safety and compliance of electrical installations. Electrical inspectors review electrical plans, inspect electrical work, and verify that it meets the requirements of the NEC and other applicable codes and standards. Electrical inspections help to identify potential hazards and ensure that electrical systems are installed safely and correctly. It is important to obtain all necessary permits and inspections before beginning any electrical work. Regular maintenance and testing of electrical systems are also essential for ensuring the safety and reliability. This includes testing GFCIs, inspecting grounding connections, and checking for any signs of damage or deterioration. Any electrical problems should be addressed promptly by a qualified electrician to prevent potential hazards. Working with electricity can be dangerous, and it is important to take precautions to protect yourself from electric shock. Always de-energize circuits before working on them, and use appropriate personal protective equipment, such as rubber gloves and safety glasses. If you are not comfortable working with electricity, it is best to hire a qualified electrician to perform the work. The color coding of electrical wires is another important aspect of electrical safety. The NEC specifies the color coding for different types of conductors, such as hot, neutral, and ground. Hot conductors are typically black or red, neutral conductors are typically white or grey, and ground conductors are typically green or bare copper. Following the color coding helps to prevent confusion and ensure that electrical connections are made correctly. Electrical boxes are used to enclose and protect electrical connections. They are typically made of metal or plastic and are available in various sizes and shapes. Electrical boxes must be properly grounded and securely mounted to provide a safe and reliable enclosure for electrical connections. Conduit is used to protect electrical wires from damage and provide a raceway for them to be run. Conduit is typically made of metal or plastic and is available in various sizes and types. Conduit must be properly supported and securely connected to electrical boxes and equipment. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. These devices are designed to trip and interrupt the flow of electricity when the current exceeds a safe level. Circuit breakers and fuses must be properly sized for the circuit they are protecting to ensure that they provide adequate protection. Electrical panels are used to distribute electricity to different circuits in a building. They typically contain circuit breakers or fuses that protect each circuit. Electrical panels must be properly grounded and labeled to indicate the circuits they serve. Wiring methods refer to the different ways that electrical wires can be installed. Common wiring methods include Romex cable, conduit, and armored cable. Each wiring method has its own advantages and disadvantages, and the appropriate wiring method depends on the specific application. The ampacity of a conductor refers to the amount of current that it can safely carry. The ampacity of a conductor depends on its size, material, and insulation type. The NEC provides tables that specify the ampacity of different types of conductors. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for calculating voltage drop and ensuring that it is within acceptable limits. Electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. It is important to stay up to date on the latest codes and standards to ensure that electrical installations are safe and compliant. Continuing education courses and professional certifications can help electricians and other electrical professionals stay informed about the latest developments in the field. Electrical safety is a shared responsibility. Everyone who works with or uses electricity should be aware of the potential hazards and take steps to protect themselves and others. By following safe practices and adhering to electrical codes and standards, we can prevent electrical accidents and create a safer environment for everyone. In addition to the above considerations, it is important to remember that local codes and regulations may vary. Always consult with local authorities and qualified professionals to ensure compliance with all applicable requirements. Testing the soil resistance around grounding electrodes is crucial to ensure the effectiveness of the grounding system. High soil resistance can impede the flow of fault current to ground, reducing the effectiveness of the grounding system and increasing the risk of electric shock. A ground resistance tester, also known as a ground tester or earth tester, is used to measure the resistance of the soil. The test involves driving auxiliary electrodes into the ground at specific distances from the grounding electrode being tested and then applying a test current between the grounding electrode and the auxiliary electrodes. The ground resistance tester measures the voltage drop caused by the test current and calculates the resistance of the soil. The NEC recommends that the ground resistance should not exceed 25 ohms. If the ground resistance is higher than 25 ohms, additional grounding electrodes should be installed to reduce the resistance. The location of grounding electrodes is also important. Grounding electrodes should be located where they are least likely to be damaged or disturbed. They should also be located where they are accessible for inspection and testing. Grounding electrodes should not be located near flammable materials or in areas where they could be exposed to corrosive chemicals. The connection between the grounding electrode and the grounding conductor must be secure and corrosion resistant. The grounding conductor should be connected to the grounding electrode using a listed connector or clamp. The connector or clamp must be made of a material that is compatible with the grounding electrode and the grounding conductor to prevent corrosion. The grounding conductor should be protected from physical damage. It should be run in conduit or otherwise protected from being crushed or cut. The grounding conductor should also be supported to prevent it from sagging or breaking. Grounding systems should be inspected regularly to ensure that they are in good condition and functioning properly. Grounding connections should be checked for corrosion and tightness. Grounding conductors should be inspected for damage. Grounding electrodes should be tested to ensure that they are providing adequate grounding. Any problems with the grounding system should be corrected promptly by a qualified electrician. Grounding and bonding are essential for electrical safety. They protect people and property from electrical hazards by providing a low impedance path for fault current to return to the source. A properly installed and maintained grounding and bonding system can prevent electric shock, reduce the risk of fire, and protect sensitive electronic equipment from damage. Remember to consult with a qualified electrician to ensure that your grounding and bonding system meets all applicable codes and standards.